Hello everybody, my name is Benjamin Thompson and tonight I'll be going through some sample solutions to worksheet number 19. This worksheet is about analyzing equations with multiple equilibria and determining their stability. The first question is simply asking us to recall the general process from a previous lecture. As such, there's no exact right or wrong answer. These are just main ideas. For me, the process of going about solving one of these questions is to solve each of the change equations separately, then to plot the resulting solutions to those equations, also called null lines, as well as the equilibrium points, and then calculating change vectors in each of the different regions that those lines separate, and then using the overall picture to determine the stability of those equilibria and the long-term behavior of the system. Question 2 here is just asking us to give a biological description of a number of coefficients in a pair of equations describing the rate of change of a rabbit and sheep population in an area. These are my answers. These are not the only ones. I think anything that conveys the general idea is fine. Okay, so without further ado, let's get on to these parts here. I think this question, as well as the final one, involve a lot of computations. I think I mistakenly focused on these too much in the recitations, when in fact tools exist that allow us to automate these computations. I'll go through some of those tonight. I think there's better use of people's time than spending like 20 minutes doing a bunch of calculations by hand when something such as Microsoft Excel or Google Docs can speed up these calculations tremendously. Okay. So before I do that though, let me just go over how to plot these things. So I think everyone has at some point seen plot. Okay, to make sure everything's consistent, let's just make sure our directions are correct. So the graph down here, S is on the vertical axes and R is on the horizontal axes. And so thinking of this just in terms of the usual X and Y, we have S is equal to Y and R is equal to X. So let's just write that here so I don't forget. And now I'm just going to make those substitutions into those equations. I won't waste people's time by doing that by hand, but instead just directly write these in. And go back and see if we can construct this algebraically. The first thing we want to do is solve these equations for just solve these equations separately. So we want to solve r prime equals 0 and s prime equals 0. Let's start with r prime equals 0. So since we can factor, since the right hand side of r prime consists of each term consists of something multiplied by r, we can factor that out. And therefore, if r prime is equal to 0, this implies either that r is equal to 0 or that this second term is equal to 0. Since we're going to want to plot both of these things, the first equation, which is r equals 0, is easy to plot. The second equation, if we rewrite it in a way that we express the variable that characterizes the vertical axes in terms of the others, it will be easier to plot. The vertical axis is s, so we want to rewrite this as s equals something. So if we add 3s to both sides, we end up with 24 minus 2r equals 3s, and hence s equals negative 2/3 r plus 8. So if I were to plot these in blue, r equals 0 corresponds to the y-axis, and then the equation s equals negative 2/3 r plus 8. This has a y or s intercept of 8. So let's figure out what the horizontal intercept is. We can obtain that, we can solve for that by substituting in s equals 0. So this gives a so we then get this line. And then we repeat the process for, actually I might just keep these equations. Repeat the process for the other one. So we can factor out the s from the right hand side of the s prime equation 2. And then if s prime is equal to 0, this implies either that s is equal to 0 or that the second term is equal to 0. And then rewriting this in terms of s, we end up with s equals negative 3r plus 15. S equals 0 is the horizontal axis, and the other equation has an s-intercept of 15, and then solving this for 0 gives us the horizontal intercept, which is r equals 5. So we end up with that equation. And then from here we can immediately visually determine the rough equilibrium points. So we know that we know these equilibrium points exactly, since these are intercepts and we calculated those. And then there's this one in the middle which we'll have to do some thinking about. Before we do that though, let's just go back onto the Desmos graphing screen and write in and include our equation. Okay. So we know, that this point here was 3, 6. How do we determine this algebraically? We simply need to substitute. We simply need to solve a pair of simultaneous equations, which are these ones here. Since we've expressed both of those in terms of s, we can just combine them. So when combining them, we end up with negative 2/3 r plus 8 is negative 3r plus 15. This gives us this. Multiplying both sides by negative 3 gives us 2r equals 9r minus 21. 0 equals 7r minus 3. So we then end up with r is equal to 3. And so now substituting I equals 3 gives us S, and that's going to give us 6. And so we indeed have that this point is 3, 6. Okay, so now we need to determine equilibria points. And this is where things can become tedious. So let's automate this. So one of the methods of calculating these equilibrium points is to choose a point within each of the 4 regions which the lines we've drawn divide the first quadrant into. We've got this region here, this other region here, this one here, and this one here. So let's just give these names in no particular order. Let's start here and call this A, B, C, and D. And so the idea is we want to select a point within each of these regions and compute a change vector there. Given that computing the change vector for these requires computing both r prime and s prime, this is going to be 8 calculations. And although the equation that gives these is in some sense elementary, it is still just going to be a lot of number crunching. So we'll automate this, but let's just go ahead and choose some points. So let's select 2, 2 here, select 6, 2 here, 6, 6 here, and then for a point in D, it's not so obvious exactly which point would be safe to choose. So let's just choose, at least one on the grid line. So let's just go with 110. So I'll just write those down again. So the point we want to test in A, the point we want to test in B, the point we want to test in C. So let's test 2, 2 here. And then for this part here, there's no, I don't think there's any necessarily best or correct choice. It's totally up to you in which ones you think will be the easiest. Okay, so now let's automate the calculation of these things. it's often like a bane among mathematicians and maybe scientists more generally when people give data and they say, look at this amazing data, and then there's actually no explanation as to where these numbers came from. Okay, enough of me like pontificating about that. Okay, so now that we've got our change vectors here, I should totally make it clear what these things are. We can just draw these. So at 2, 2, okay, in a similar way in how I used the graphing software before to normalize all of the vectors, that is to draw them in such a way that they had a consistent length. It'd be a good idea to do that here. For instance, the change vector for the very first one is 28 and 14. So if we would actually draw that to scale, starting at A, it looks like we would have to draw something about this big. Right, and that's absurd. Like we don't want to do that. That's not really, like, the size of it isn't the important information that's being conveyed. What's important is the direction of it. And so since the change vector at A contains both a positive R prime component and a positive S prime component, generally it has something that, it has that kind of direction. Might make it just a little larger. Okay, so that's A. B, let's think. The change in R prime is positive, but the other change is negative. And so this is going to be pointing in that direction. At S, we've got a change vector where both components are negative, so that's pointing in this direction. And for D, we've got something where the horizontal component is negative, but the vertical drone is positive. Okay. And so given that we've drawn the null lines, and given that all of these functions are continuous, we can then infer something about the general direction of all of the change vectors within a region. What do I mean by this? So I claim that all of the change vectors in this region A point upwards and to the right. So if it were the case that some vector within region A pointed to the left instead, this means that we would be able to find like a path from such a point. Say that point was, I don't know, up here to A, and then since all of these vectors are continuous, it means that analyzing the horizontal component of all of those intermediate change vectors, the change vectors like cannot just jump from a positive number to a negative number. They need to go between 0, and that means that when they go through 0, they would be they'd be going through 0, and the point at which the point at which one of the change vectors is 0 is by definition a null line. And so if it were the case that the vector changed direction within this region, we would expect to see a blue line within this region. But there is no blue line in this region because we've drawn all of these. The blue lines are the ones up here. And a similar argument, that is like continuity, and the fact that we've drawn the null lines explains why all of the change vectors in this region here should also point upwards. If one of these was to point downwards, then we would be able to find a point in here in which the change vector, in which the vertical component of the change vector was equal to 0. That would correspond to an orange null line, and by considering things within this region where we've drawn all the orange null lines. Okay. So by extension, this also means that when we get to these null lines, it means that something is changing, and we can see this going from region A to region D. Although the vertical component of the change vectors is still pointing upwards, the horizontal component changes. Everything here is pointing to the right. Things in here are 0, and now everything here is pointing to the left. Similarly, everything here is pointing upwards, but everything here is pointing down. And and sort of doing, crossing two of these, two things are going to be, crossing an orange line here corresponds to the vertical direction of the change vector switching sides, and crossing a blue line corresponds to the horizontal component of the change vector switching sides. And so going from region A to region C, we can do that by going in a loop like this. We're crossing an orange line and a blue line, and so we would expect both the horizontal and the vertical line, both the horizontal and vertical components of the change vector to swap, and indeed that's what we can see happening. Okay. That was perhaps like a bit of a tangent, but I think still useful to know, and at least it helps me conceptualize these things. Okay, so now we have an idea of all like what's happening with all of the change vectors in here, and as a sanity check, we so then in order to determine the stability, so then like we've essentially determined the stability of these things. We now just need to formalize this. So let's just write down a list of all of them. All of the equilibrium points. And so at the origin we've got an unstable equilibrium. Any small perturbation from that point, like we'll be on a trajectory that goes far away from that point. At 3,6 we've got a saddle. Although some vectors are pointing towards it, these regions here are pointing away. And so eventually, even if something is approaching it this way, it will probably sort of swap over to the other side and then immediately head upwards or downwards. And then these other points are going to be stable. I mean, I guess like if we wanted to be like totally sure of things, we should just think about what happens to some of the change vectors on the horizontal on the r-axis or the s-axis. But again, like the same argument regarding how the components switch when they cross lines can apply here. Since this change vector here, both components are negative, when we head to this direction here, although the vertical change is now equal to 0, we haven't crossed any blue lines, and so the change vectors here are going to be pointing to the left, and then that really seals the deal that this part here should be a stable equilibrium if we've got arrows pointing that way. I'll just make it clear. And likewise, a similar argument for why the vector up here needs to point down. We can find a continuous path going from this change vector to this one here, which doesn't cross any blue lines, any orange lines, and hence the overall vertical direction of that is going to stay the same. That is, it's going to be pointing down. Okay, so yeah, I said this was a very long question. We're nearly at the end of it. We now just need to describe the long-term behavior of the system. I won't waste people's time by spending 5 minutes writing down like an exact description. I'll just verbally say it. So we can say that like at all of the equilibrium points, there's going to be no change. By definition of these things being equilibrium points. In all other regions, points are eventually going to end up at one of the two stable equilibrium points. That is, things are going to end up there or over there. Okay, biologically, what does this mean? Each of these points corresponds to points where like either one of the species is completely extinct. This point down here corresponds to the values for which r is equal to 0. That is, all of the rabbit population will become extinct, but there'll be a lot of sheep. Likewise, this point over here corresponds to the point where all of the... Oh, I was really silly. Pardon me. I got that around the wrong way. This part here, s is equal to 0. So this corresponds to the situation where all of the sheep die and there's loads of rabbits. This part over here corresponds to the situation where there are no rabbits, but there's lots of sheep. So eventually one of the species, I mean, unless it's the extremely unlikely situation where like the number of the population of the animal stays exactly the same over the entire amount of time, there's going to be some slight perturbation, and then immediately things will converge to either one of the 2 points. Okay, so that was question 2. Question 3 involves... In question 3, we're looking at the same equations, but from a slightly different perspective. Part A is just asking us, without making any computations, what do the change vectors on the R null line and the S null lines look like? I've pretty much described this already, right? Since these correspond to the exact values for which one of the components is equal to 0, this means that all of the vectors along these null lines are either going to be pointing purely up and down or purely to the left and the right. I guess I did sort of write it down more concisely there. Okay, and now we come to part B, which is another computational part. So now we're asked to compute a bunch of change vectors on the R null line and the S null line. So let's do this. So we'll once again just use the Google spreadsheet to do this. So the ones we want to compute on the R null line are 1, 22/3, and 6/4. And for S prime, we want to compute 2, 9, and 4, 3. So then let's Okay, back to the tablet. Okay, let's just copy all of this to the graph. Well, where are we going to put? Okay, I mean this is a YouTube video, right? So if you desperately want to see what I wrote here before, just save the current time spot and jump back. And now we want to plot these. So let's choose another color. Let's do these ones in pink. That's a bit misleading. Oh no, I mean that's not misleading at all. These are okay. So the first one is so the first two are null lines of R, which is the blue line, and so these points are at R equals 1, which is this one, and R equals 6. The other two are null lines for S, that is the orange line, and these are the points at R equals 2 and R equals 4. Okay, now we can draw on the actual change vectors at these points. Let's use a different color. Let's use light green. So for the first one, we end up with 34. So something that points in that direction. Next one is negative 28. So it's pointing down. Then we end up with something that points to the left. And then maybe I should just actually, yeah, maybe I think this is a more logical way of doing it. Just looking analytically at these directions, we can plot which directions they're going to go, and then immediately add these to the graph. So we've done 1, 2, 3. We just need to do the last one, which is this one. And as we can see, these change vectors agree with the directions of the purple vectors, which we drew earlier. And I think that was all that was needed for part B. Yeah, compute these, which we did. Use these vectors to confirm the direction of the second, which we did. Okay, sweet. So now let's move on to the last question, which is question 4. And in this one, we need to do it all again. Yay. Okay. Let's, okay, so we'll just do the same thing, solve these equations, we'll then plot them again. Equilibrium points, all that jazz. It's like, this isn't, if I had to compare this type of mathematics to a musical genre, like I'm not necessarily sure that it would be jazz. I don't know. Okay, so we end up with d prime is equal to this thing. We can factor out the m here too. Decimals kind of freak me out, so let's just we can rewrite these when it comes. I mean, hence why I'm not an analyst. So this is why we can. So in the next part we can simplify these. So if d prime is equal to 0, either d is equal to 0 or or we end up with the second term being 0. So if we factor out 100, we can write this as 30 minus 2d minus 5m is equal to 0. And there's no graph on this page. We get to invent it. So we need to be careful here again regarding the direction of like, you know, whether M or D corresponds to the vertical or the horizontal axis. So what are these things? These are things like, these are deer and mice. So maybe let's we can give like the we can give the small guys a chance to be tall and put them on the vertical axis. Okay, so if this is the case, we now want to express M in terms of, okay, I'll just do the similar thing of making it clear at the top here that Y corresponds to M and X corresponds to D. So we want to write this equation here in terms of the vertical variable, which is the M. So, you know, multiplying everything by 100 here and then adding 5m to both sides gives 5m equals 30 minus 2d, and hence m is given by 6, let's write it in this direction, negative 250 plus 6. Let's go ahead and plot these. D equals 0 corresponds to this part here. The m-intercept of the second equation will be 6. Let's just put that there. And let's solve for the horizontal intercept. So 0 equals negative 250 plus 6. Then 250 equals 6. So D is equal to 6 times 512, which is 15. This graph already looks like it's going to be slightly out of scale. Maybe, so let's move the 5 down to here, so then we can put the 15 there. No, even that looks a bit out of place. Okay, that looks better. Okay, and now let's do it again for the second equation. So then if m prime is equal to 0, this implies m equals 0, or that 1 over 100 times 20 minus 4m minus 2d is equal to 0. Adding 4m to both sides will give 4m equals negative 2d plus 20. Everything here, so then dividing by 4 gives us m equals negative half d plus 5. So the so this then suggests that the y-intercepts are going to be the same, and so setting this to 0, we can solve. So 0 equals half d plus 5. So d equals 10. Okay, and now let's use our graphing software to graph these and you know, give ourselves some reassurance that we haven't made any silly mistakes. I should first of all just tidy things up a bit. Okay. So, let's see. Okay. Let's go ahead and fix that. So apparently the blue line should have a intercept of 6 instead of 5. Let's just convince ourselves of this. So solving that one with m is equal to 0, again, we have this is equal to this, so 2 5d equals 6. So d should be 6 times 5 over 2. Oh, I'm being silly. We already... that's calculating the 15 intercept, which you know is correct. Oh, so this is a bit embarrassing. I somehow just looked at that and thought that number was 5 instead of 6. I didn't know my brain works so poorly at 10:30 at night, but apparently it does. Okay, that's a 6. Either that or it was just the watching one episode of a Netflix show. I'm too ashamed to admit today, which was a reality TV show. Boggled my brain for the rest of the night. Okay, So this is so we're kind of done for the plotting part. Now we just need to determine the equilibrium points. And so it would actually be good just to right. Oh, I lied when I said I had finished plotting. I forgot to plot the line m equals 0, which just corresponds to this part here. So the intersection points are the points where both the orange and the blue lines cross. So we've got 1 point there, 1 point there, and that's going to be it. We've only got two. Pardon me. that is the origin's always a point too. So that gives us 3 equilibrium points. Let's just write them out here again. So you've got 0, 0, 0 and 5, and 15 and 0. Okay, so now we need to determine the stability of these things. You know, I could, I guess, for the sake of completeness, it's good just doing these. I'm not going to do these by hand. We'll just do the automation of the spreadsheet. So once again, let's just pick some vectors in these regions. So we can choose a point in here, say a point there, and say a point here. Let's write these out with a different color. So the point, I should just label these regions like I did the other ones. Let's call this A, B, and C. So we need a point in regions A, B, and C. For point A, let's choose this to be, I don't know, like 1, 1 should be fine. For B, let's go with maybe something just above 10. So you can choose 10 and then 1. And C, it looks like I chose that to be 10 and then 6. Okay, so let's go back to our spreadsheet now and to business. So yeah, so these ones corresponded to D and then M, and then D prime and M prime. Okay. So in a similar way before that, I just drew cartoons of the directions of these things first and then put them on the plot. Let's just go ahead and do that. Let's just be fancy and use a different color. We can use, let's use this thing. For these ones, so for these vectors here, both components are positive, so the change vector is going to be pointing in that direction. The horizontal component here is positive, but the vertical component is negative. And for the other one, both components are negative. So putting those on, something that goes like that, something that goes like that, something that goes like this. As a sanity check, let's compare these with the okay, so now we need to determine the nature of the equilibrium points and the long-term behavior of the system. So the point at 0, 0 at the origin is unstable. Everything's going away from it. It's fine for me to include a dash there. And then what about this positive, this vertical intercept point? It's also going to be unstable. If anything around here slightly goes into this, if this point were to go down here, it would go into this region and then get sucked into that region. Likewise, if it goes up, it's already in that region. So it's unstable here. And then for this other point, we end up with something that's stable. Things are going towards it, and again, just like as a sanity check, what happens to the vectors in this area here? Well, since there's a path from a vector here to this vector up here that doesn't cross a blue line, since crossing a blue line here corresponds to the direction, the horizontal direction changing, it means that the horizontal direction of this part here will be the same as the horizontal direction of that. That is, it's going to be pointing to the left. And so if the change vectors are going in that direction and in that direction, then yeah, this is stable. All right, we are one question away from completion. We now just need to determine what happens, what the long-term behavior of this system is. What are the cases? If we start at an equilibrium point, by definition, nothing's going to change. And then for any other point, as time goes on, we're eventually going to end up at the final equilibrium point, at this one down here. Again, I could spend like 5 minutes writing this as a sentence, but I assume like everyone's comfortable with me saying this, and I think YouTube already has subtitles as well, so that's automatic captions. So maybe it's just good to think about what this means biologically and make sure this makes sense. These are representing these animal populations, and this point down here corresponds to m equaling 0, so that is the mice population going extinct in this area. And so even though we wanted to give the little guys a chance by putting them on the vertical axis and making them higher, the deer end up winning. And I guess biologically you could sort of you could say the deer eat a lot more if they are eating resources. Maybe just the fact that yeah, like the consumption volume of product of the deer means that yeah, the mice won't have much left to live on. But yeah, so that brings us to the end. Yeah, I hope you found something useful from either how to adapt yeah, I hope everyone has a great weekend. Out.